In the intricate tapestry of life, woven with countless threads of molecules, a captivating tale unfolds, which includes a tale of molecular and biophysical modeling. At the heart of this tale are the receptors, the gatekeepers of our cells, existing in a delicate balance of two biophysical states, active and inactive. We discovered that this occurs by an electrostatic switch that is pH-dependent. We called this switch cysteine modulation. This balance is not haphazard, but a meticulously controlled dance, dictated by an electrostatic switch mechanism. Picture a simple balance in horizontal equilibrium. The two scales represent the active and inactive states of the receptor, constantly teetering between each other. Add an external force, a drug molecule perhaps, and the balance tilts or shifts. From our molecular modeling, we deduced that receptors must exist in two biophysical states, which are the active and inactive states. This is shown in the figure. Delta RH changes these states in a quantifiable way. Here's where our electrostatic switch comes into play. This switch mechanism is our delta RH in the figures. When the delta RH shifts, the switch flicks, activating or deactivating the receptor. The delta RH functions like a switch that can turn a receptor on or off, since the two states of a receptor might be functioning as a poised chemical equilibrium. This is akin to the two ways we can tilt a balance that we talked about earlier, causing the balance to lean towards one side. Thus, we began by considering the following equations in analogy with the balance. To understand this mechanism further, think of the drug-binding molecule, labeled as D. The binding of D to the receptor is what triggers the switch, delta RH, nudging the receptor from an inactive to an active state, or vice versa. The drug-binding molecule is labeled as D, which binds to the active state as DRH and also binds with the inactive state as DRL. Instead of the delta W that we solved for the balance, we solved for delta RH, which we refer to as the net shift. This dance between the active and inactive states, influenced by the binding of D, is captured in the concept of net shift, or delta RH. To describe this relative binding as chemical binding, we introduce the Langmuir expressions for chemical binding to each receptor state. The Langmuir binding expressions are well-known expressions for describing the binding of one molecule with another. This led to a full expression for delta RH, the net shift. This equation for delta RH, the net shift, was tested against several classical dose-response curves for receptors and found to fit them very well. The net shift parameter appears to directly relate to the efficacy of the molecules. This was a significant and exciting finding. This net shift model describes the full gamut of all possible receptor responses as shown in the figure. This is the story that has unfolded for over 30 years. The work has been experimentally tested many times and in multiple ways, and it continues to model receptor responses in surprisingly direct and relatively easy ways. As we reach the end of this exploration, it is clear how the net shift model serves as a potent tool in describing receptor responses. But its implications stretch far beyond the microscopic view of our cells. That is the story in a nutshell. The fact that this delta RH or net shift model describes sensory receptor responses is quite remarkable. It helps us understand the biochemical connections of all life and the broader chemistries of the universe. From the humble receptor in our cells to the vast cosmos, the net shift model weaves a narrative of balance, interaction, and response. It stands as a testament to the interconnectedness of life and its molecular underpinnings. And in understanding these connections, we find ourselves a step closer to deciphering the language of life, one molecule at a time. This story is available as a book, Origins of Life Sensoria, on Amazon, shown in the link below.